Okay, hello everyone. Welcome to the Penn State Startup Week event. I'm delighted today to introduce Andrew Wienert, who is a 2009 Penn State graduate and who has been at the MIT Lincoln Laboratory since graduation, working on aviation and disaster response problem. And today he will be talking about what is data science, the potential of the low altitude disaster imagery dataset. And because this is a webinar via Zoom, so if you need to ask questions, please feel free to use the Q&A function at the bottom of the screen. And you can also click on raise hand so that we can see you that you have a question. And Mary will be moderating the questions throughout the session. Okay, and welcome, Andrew.
Thank you. I'm gonna go share my screen here. I'm gonna probably talk for about 30 minutes or so, and then answer questions and have discussion. And so feel free to put them in the Q&A box. And depending on how the flow goes, if we see a bunch, we can pause, after I finish talking about something, or we can wait to the end. So just don't be shy asking questions and using the discussion. So what is data science? So when I graduated, make sure I can see that. I could potentially see if you raise your hands, but I'll be focusing presenting. So I will watch out for raising of the hands. So what is data science? When I was at Penn State over a decade ago, data science wasn't really a term of art. There was certainly no degrees in data science. This is before deep neural networks really gained traction. This is in early days of kind of Web 2.0. And so the way we looked at the world 10 years ago looks very differently today. And data science was born out of that. And so, for a good chunk of my career, I never really assigned or titled myself as a data scientist. But it's certainly a term that I can apply to myself, and I am comfortable applying to myself. The problem with many of these terms, though, is they often lose a lot of meaning. What is actually data science? How do you explain to somebody who has no technical, no ISD background, what you actually do? What's your day-to-day job? It's not immediately self-explanatory. And so a counterpoint is, well, if someone says they're an accountant, okay, I know what an accountant does. Oh, I'm a lawyer. Well, there's a lot of different types of lawyers, and they do different things, whether in the courtroom, or they may never attend the courtroom, but they're still a lawyer, and you kind of immediately get that. If you had to walk into an elevator and someone asked what you did, and you said a data scientist, well, what is that? And often what you see and learn, or you will learn, is what you think data science is, what you think you will do upon graduation is somewhat correct and somewhat not correct. And so today I'm going to try to give you insights of, really what is kind of the day-to-day job that I do, but also how we look at problems. I think one of the key elements of data science in particular is very much like a systems engineering, or at a very high level requirements and validation exercises. It's not turning the crank at all times. It's really saying, this is why I did something this way. So to start, here is a picture of flooding. This is, from a real disaster. I believe this is from Hurricane Florence in the Carolinas a few years ago. And this was collected by the Civil Air Patrol. And the Civil Air Patrol, they are the folks who fly small aircraft like Cessnas, predominantly with humans taking photos with their fancy cameras of a disaster. And so let's think about this for a second. So we have a use case that we care about. We want to respond to disasters. And we have a data set of raw imagery. And we don't necessarily know right, from a computer vision standpoint, we don't necessarily know what images were collected. I didn't take these photos, and I have effectively no say in how the Civil Air Patrol collected these imagery, but the content of this imagery is relevant to me, and it's relevant to many other people. And so simple questions, where is the flooding? This answer could help answer that. What is the status of the power lines? Is the power grid disabled or impaired? And if we zoom in, there are power lines in this image. What is the status of the roads? Okay, we can answer that. And these are very much kind of that first order, hey, I want to be able to answer questions. Well, what about, can I move? I care about maybe a community. They're cut off. Are they cut off? Can I move supplies to them? Can I move supplies via a truck, or do I have to bring in a helicopter? And so now we're talking not just, is there flooding, is there roads? Well, is there flooding over specific roads that I care about? And so this is inherently the difference between, or at least I believe the difference between data science and kind of traditional computer vision or computer science. Computer scientist would say, I am going to make a really awesome algorithm, a really awesome classifier to tell if there's flooding in this image. And that's their focus, right? They're very focused on the mathematicals, the neural net training, the classification training. And as a data scientist, you certainly need to understand underneath the hood, what this classifier is doing, but you don't necessarily are the, de facto expert on how you train. You can speak the language, but you're not, completely fluent in it. On the other hand, if you say you're an analyst, and this could be a business analyst, this could be an Intel analyst, similar to, say, an SRA degree. I care about moving supplies from point A to point B. And so they need to know where the flooding is. They need to know the state of the road, but they don't necessarily care how they learned that. If you made a map to them and said, here is where flooding is, and these are the accessible roads, that's all they really care about. Because their job is to move supplies and do the logistics. Data science, I believe, fits in the middle there, where you want to be able to look at this image and say, okay, what type of information can I glean from it? And then how do I extract that information to make it useful? So here's another photo. This is also damage, disaster. It shares many of the high-level kind of contextual labels you would assign to the flooding. Flooding is a disaster. This is post wildfires in California a few years ago. So this is also a disaster. There is also damage in a very general sense in this image as well. Here, we're not looking at flooded roads as damage. We're unfortunately looking down burned down homes as damage. And so once again, kind of tying this back on how do we think about this and approach the problem, damage is something we care about, but what damage looks and feels like is very, very different. And so do we have to develop different classifiers to quantify damage differently? What is actually damage? How do we learn what damage looks and feels like? So you say, okay, right, we're talking about this, Google, Amazon, Microsoft, all the tech giants has these awesome computer vision services. Facebook, right? They market all the time. Look, we could do image recognition. A key thing to remember though, is that many of the commercial companies are focused on what? Commercial use cases and making money predominantly, right? If you're going to invest in a technology, you're going to want largely a return on the investment for most businesses and organizations. That's not unique to the tech giants, right? That's why we do things. If you're a startup, odds are you're in a startup to at least pay the bills. And so you need to invest in technology to pay the bills. And then if you want to make a profit, go make a profit. Even if you are a nonprofit startup, you still need to pay the bills. So as a human, we can look at the image, the flood image, and we can look at this image of rubble. And as a human, we can immediately say, yeah, that's flooding, that's burned down homes, this is bad. There is information in this images that I care about and that I was immediately cued into as a human. Let's look at the Google Cloud Vision API for that rubble. Well, they're not wrong. Yes, that photo was taken during the daytime. Yes, there are trees. Yes, there is a road surface and there's a neighborhood. Is that the type of information that we care about in terms of disaster response? We can keep scrolling down, scrolling down, scrolling down. Yes, it is aerial photography. Yes, there are buildings. And this is not wrong. And this is, from a service geared towards the commercial market, or really for not the disaster market, which has a very different feature space than pretty much anything else. The system performs less than ideal. And it's not, their necessarily fault, right? It's you trained a system to do something and we're presenting it with data that it wasn't necessarily trained to do. And so not just to call out them, here is the Amazon recognition service as well. Similar things, landscape, scenery, aerial view, urban. These are all 100% correct answers. The system did as it was designed. However, as someone interested in disaster response and humanitarian assistance programs, these systems are not meeting my needs. So what do we do? So I'll quickly pause there. If anybody has something in the Q&A, if not, I will keep going. All right, I will keep going. So what do we need to do? I'm going to resume sharing. What do we need to do? We need to teach the AI what disaster looks like. We need to teach it on what features of interest that we care about. And so as a computer scientist, how do I feel? I will get that to the end. What do we need to teach the AI to do? And so similar how we started looking at a flood in the rubble, what are things that we care about? Well, we care about roads, we care about floods, but I really care about when roads are flooded. And so we built a data set. And so the data set is freely and publicly available. Here is our GitHub page. We can put this in the chat. And so you can be working off of this if you want to follow along. For your own interest, right? We are giving this out for free. And I know I talked about paying the bills and everything. I will get to that at the end about kind of a unique role that I play at Lincoln Laboratory. So we built a data set. And we took this low altitude imagery collected by the Civil Air Patrol, which they released. FEMA paid to keep Civil Air Patrol, and they were releasing the imagery to the public domain, but it was raw, it wasn't annotated. And so as a data scientist, it's like, hold up. There is 500,000 images dedicated to a use case that I care about in the public domain, and all I have to do is annotate it. Was super exciting. One, because we're not contriving or making fake scenarios. This is real operational data. And so all the ugliness that you get with real data, whether or not there's sun glare, it's a human taking the photos. So the way they take the photos will different, time of day, smudge, all of it. is in this. And so it's from a data set standpoint, it's very robust and noisy. And so we won't necessarily overtrain our algorithms. And so we took it and said, okay, well, what are we going to do with it? How are we going to label it? And so we came up with this hierarchical labeling scheme. So when we annotate it, we paid Amazon Mechanical Turk workers human tasks to annotate each image, and that costs money. Additionally, we chose and we promote that while Mechanical Turk does not have, or many of these crowdsourced services do not have a kind of minimum wage requirement, we wanted to put funding out where that was the equivalent of the US federal minimum wage. Once again, it's definitely not, a large sum of money, but most Amazon mechanical workers are on average paid $2 to $3 an hour, potentially less. And so coming in with $7+ an hour was, from our standpoint, much more resource intensive or costly than many other efforts, but it was also the right thing to do. It's not, we definitely would have not felt right talking about a disaster response data set to help people when people are working on this for potentially pennies. And so with that, and regardless of the wage we did it, we still have a finite budget. To completely annotate all these images and everything would have cost millions of dollars. Last time I checked, probably $3 to $5 million to get everything. And new imagery comes every year, so it's a big problem. So what we did is, okay, what is that first high-level thing we care about? And so we first asked, what are the 5 course categories? And we're simply asking, is there water in this image? Yes, no. And so phrasing that question is another part of data science. There's a lot of different ways to annotate the imagery, but what is the way to be most effective and get the answers I care about? So we, as I mentioned, we really care about, focusing on teaching AI, ML. This is what a disaster or damage looks like, really looking at that logistics use case. And so by simply asking, well, is there damage or water in this image? We're not asking, is there roads or anything, but it enables us to very quickly whittle down to a subset of images that are more relevant. I don't need to teach an AI what necessarily a car in a nominal situation looks like, or what an aerial perspective looks like. The commercial sector, the open source community has already solved that. And so if they said yes into one of these high level ones, we would then go down and then to re-ask the question, well, if there was damage, is it just miscellaneous? Is there flooding, landslide, washed out debris, smoke, or fire? And so what's important to note here is that the high level and both the specific level have both things and stuff. Things are exactly what they look like. They are very discrete objects. A thing is a car, a house. It's a label. And often when we think about many of the tasks that your homework assignments, or many tasks if you do upon graduation, are very focused on discrete things. I want to put a bunch of data input and I want to get something that's very black or white out. The challenge with the disaster response space and many other places, there's a lot of stuff. Stuff is this more nebulous block that are not easily labeled or identified. So flooding is a great example. You can draw a bounding box around a house. How do you draw a bounding box around a flood? Flood could be in many different parts of the image. It could be unclear what parts are potentially flooded, if there's a foliage or something, or damage. So if I tell you label the house, great, you would likely put a whole, full box around the house. If I ask you to label damage, Well, suppose the house has blown off some of its roof and maybe some of the windows are broken. When you label the damage, how do you do that? Do you draw a box around the entire house and say damage? Do you draw bounding boxes around each individual window? Do you draw boxes around a set of windows? Maybe you draw a box for the windows and then a box for the blown out roof. And this is really where the problem with stuff is. And so when you go to the machine learning, when you go teach the AI, you need to be kind of both consistent on saying, here are many examples of the same thing, so they learn what that looks like, but you also then need to introduce that variability so you don't overtrain the model. How you label stuff is really the former, right? I need to be consistent on this is what damage is. And so part of that task is us, educating and communicating to the workers, this is how you should label damage. But it also goes farther back up here where even if they mislabeled it or a way we didn't like it or a way we didn't expect, let me tell you, they will label it ways you didn't expect. And that's more of a onus on us than them. We still know there's damage and at a high level semantic content. And so you really have to think about the whole problem. And we're just talking about labeling the data set here. I can talk for hours on simply this effort. The other thing we did is there are commercial and open source classifiers, and we ran it through there too. And then lastly, this is imagery, right? There is metadata underneath the hood. And this is not something that when we look at this as a human, that is, we don't see the metadata here, right? We can load into a metadata viewer, but as a human, when we immediately see this image, right, we see an image of flooding. And so this is really where some of the advantages of machine learning comes into play, because we can then say, okay, what are additional information that as a human that isn't necessarily as accessible or readable to us? Even if I told you that, this is a specific latitude and longitude, that, numbers of latitude and longitude will mean something to you as a human, but it's definitely in a format that's more amendable and more readily accessible for a robot to take. And so here are, once again, the examples of the labeling scheme and examples for some of the metadata. So we built this data set, and then what? Where does it go? Well, we can then use a variety of machine learning as a service. So there's Amazon, BigML, Google, IBM, Microsoft Azure, et cetera. And so we have a data set that is unique to my use case. That doesn't mean I have to do the whole AI ML training alone, right? I don't have to completely reinvent the wheel. And this is another really part about kind of the difference where once you get to data science, it's really, or upon graduation, how can you be efficient and how do you tackle this problem? Where are your strengths and where are your weaknesses and where are you trying to, maximize your resources? And so for us, we need to maximize our resources in labeling this data set. But at this point, then it's, in many ways, it's now a somewhat traditional computer science problem. I have labeled data. I'm going to go build a classifier with that data, and then I'm going to evaluate it. And so I won't touch upon that here. And you can find that out here on the README and everything. And so what's next? So we have a data set. I have built it as a researcher with my colleagues. Where does it go? How do I maintain it? And this is, so you see the GitHub page. And so we've released the code and documentation, and this took us a lot of time to write that documentation. We we helped fund a Penn State capstone project last year to build out a basic tutorial. So we have a tutorial, and you have to communicate, okay, what do you need? Okay, this is how you set things up. Okay, you're going to need to install these Python packages. Here's an example. Here's an example of some of the data, what it looks like, and so forth. So that's part of the data science.
So Andrew, there's a question in Q&A asking whether the wrong screen has been shared by chance, because they are seeing the flat image only on the screen.
Let's try it this way.
Yeah, maybe you have to share again.
Do you see the
not
an image?
We can see, yeah, great.
Cool. Yeah, so here's a tutorial. And yeah, so that's part of this. We got to communicate this. Where does the data set live? And so someone's got to pay for the server cost, right? And there are certainly programs that you can apply to host it commercially. Depending upon your organization or institutes, you can host it there. Depending upon the size of the data set, there's open source data set repositories. And so taking that is another really big part of that. Because the raw data by FEMA was already hosted in the AWS cloud. Also because we applied to a variety of programs, they had something called the Open Dataset program that we applied to and were accepted. And so the first 2 years of the hosting of the program was covered by the cost of AWS. And so we then registered in the registry of open data on AWS. You can see here, again, the licensing, documentation, here are examples, right? These are all things that, we had to populate this, but we also had to find out the best way to communicate it, and then you can go grab the data. You need to be comfortable with Git and GitHub, because this page, we forked one of their registries, and then we made our contributions to it. So Dataset, and then LADI should be here. LADI.yaml, and right, so then we populated the information that you see on this nice, pretty, easily digestible website is simply something that we contributed to their GitHub repo here. And so this is what the raw form looks like. This is honestly a big part of the data, in my opinion, a big part of the data science. It's not simply providing and making the content, but making it available. So we have that. You could then start working depending on who's, okay, I have a data set, but I want others to use it. And so that's part of the engagement that, and from the College of IST perspective, that's a little bit more of the business development side. And so we worked with NIST, the National Institute of Standards and Technology. They have this TrekVid computer vision challenge, and they adopted the LADI data set for one of their computer vision tasks. And so we helped work with them to say, this is the development data set. This is how you notice this looks very similar to the README we wrote. That README I wrote was publicly available and licensed under a permissive open source license. So it was very easy for NIST to take much of our own language and adopt it to their needs. And then this is now the information on how do you evaluate that computer vision, open issues, and things like that. And so now we've had 1 year of this, and about 5 or 6 academic papers were written based upon this. So we're seeing how other people build classifiers. It's not simply us being kind of the sole people trying to build a computer vision classifier. It's now more of a community effort. The last part, as we are watching the clock, is a lot of what I talked about here is the data set, and it exists. The data set exists now. It's been used. In 2019, at Startup Week, I gave a talk on building the data set. So the data set was in development about 2 years ago. And I would say COVID, even though working remotely has not slowed us too much, it takes time, especially for about use cases that you don't want to screw up. it is one thing to potentially mislabel a image of a cat or a dog, or if I mislabeled, if a facial recognition algorithm for a social network, say, mislabeled a picture of me as my brother, right? It's not that big of a deal. And so that we are much more tolerant of mistakes or incorrect answers. When we talk about disaster response, we are extremely intolerant of incorrect answers. One, from both an efficiency and operational standpoint. If I'm trying to allocate search and rescue teams, and I say, well, here's an image, here is a point on a map that's under flooding, and I see homes that need to be surveilled to pick people up. And then we, fly the helicopter that costs fuel and money with rescuers, which costs their manpower and time. And that region isn't really in distress. That is very bad. That is very, very bad for the response and very bad for the survivors and victims. Additionally, in terms of technology adoption, this is all still new technology, and the disaster response, public safety sectors are often a little bit slower to adopt technology. And so if we come in and say, we have this classifier and it's going to do all these great things, and we oversell it, and they actually deploy and they find out, every 2 out of 10 answers are wrong, they're going to stop using it because they say, this is wasting my time. And then they're going to be turned off from the technology, and you're going to, maybe years again to kind of rebuild their trust to even try again. And so we do have classifiers. We have prototype classifiers. Right now, our performance is depending on how you slice and dice it, we're about 80% accurate for flooding. We are not ready to go into an operational capability, right? 8 out of 10 for this regime is not appropriate for an operational capability. Now, 8 out of 10, is this something for a shadow mode where it's not in the critical path? Yeah. Is it a place where we say, okay, we are on to something here and we need to further, develop resources to get to that 90, 95%? Yeah. But 80%, depending on what use case you are, can mean very different things. And so to kind of wrap this up, page up. What is data science? If you're looking for jobs and I want to do data science, what does that actually mean? Again, I said it means nothing. Well, I work at Lincoln Laboratory. We're a $1 billion a year nonprofit laboratory. Here's our front page. It doesn't scream data science, right? We have a pretty picture. We just turned 70. This is our byline, technology and support of national security, and then recent news. Okay. I work in the air traffic control group. We improve air transportation safety, and I work in surveillance systems, a very vague name. And our group develops integrated sensing and decision support systems that enable safe and efficient air and surface transportation. It's vague. I know it's vague. The lab knows it's vague. That doesn't scream data science, right? I just gave a talk about using computer vision for disaster response. That doesn't say that, right? It says it, right? What I described is very much an integrated sensing and decision support system. And so what I'm trying to get apart here is, really don't fret if you look for job postings, if you look for grad schools that don't scream data science. I'm a firm believer that, majority of the technical work these days can be constructed as data science. And so one, understanding, like I said, do you feel comfortable that you are a data science is really a question on you, step one. And then step two is, when you go apply for jobs, when you apply for grad school, speak their language. To you, I spoke, as a graduate of Penn State today, speaking about what I think data science is and how you market yourself and everything like that. If I gave this exact same type of talk and hit the exact same topics and contents, but I gave it to my colleagues at Lincoln Laboratory, I would give this talk very differently. The words I would use, the perspectives that I would talk about would be very different. And so even when we're looking at, say, this image, knowing your audience is a big part of this. And so while as a human, we all look at this and say, yes, there's flooding, but the way you speak to it, once again, is kind of that key part of data science. And I know it's something they talk a lot about in SRA as well. It's know your audience, because you want to convey your message. And hopefully I conveyed the message well to you today. But you have to, once again, think about the big picture, think ultimately what you are trying to achieve, but also what your audience is trying to achieve. And so with that, it's 11:11. I spoke for about 40 minutes, and now I will take the Q&A.
Okay, the first question that we have is, how do you feel analyzing the data and help with responses?
So it's, I would say it's a mixed emotions. It is not fun looking at damage and flooding and destroyed homes, right? You can say this image of the flooding, you can kind of remove yourselves, but with the pictures of rubble here, right? Like that's someone's home. And this is honestly not even nowhere even near some of the worst images I've seen. So fun is not the word I often use. Rewarding and engaging, absolutely, right? I enjoy that I work for domestic issues, whether that's for disaster response or really a lot of these tools here are, ultimately I want a drone to fly out ahead of helicopters and surveil the area and say, here are victims. And so I need to, one, teach the drone, the AI, how to find damage, which is what we talked about today. But then a good chunk of my job actually is working on how do I get that drone to safely fly in the airspace and not be a nuisance. And so what you'll see if you go to the Lincoln Laboratory website is, yeah, we absolutely do DoD and defense research. I made a choice that I really want to focus on domestic issues. And so I do enjoy and respect that. And I think one thing that positive emotion, I don't know the word, is that you can do technical STEM work and you do not have to go to a defense contractor. I know when I was an undergraduate, I assumed I would end up, at a defense contractor or a large organization like that. That is certainly not the case. I enjoy that I, work on problems that, help us domestically and problems that, can be applied from a humanitarian assistance or an international standpoint. I would say, not completely going to tangent here. A few years ago, after Hurricane Maria, about 9 months after Hurricane Maria in Puerto Rico, the laboratory flew a 3D sensor over the entirety of Puerto Rico to map the recovery effort in post-disaster. Due to the sensor on that aircraft and due to our mission needs, we had to fly at night. And each mission was about, hopefully, about 8 hours long. And so it took us a month. We planned to do it for a month. I was going to be in the second wave to go in. And so I was actually in California at the time at a conference being like, okay, right, I'm going to fly to Puerto Rico. I'm in California. I'm going to shift my schedule. I'm going to be on the aircraft at night. This is right. I'm making on my flight to Puerto Rico. I got a call from the flight crew and they're like, we need you to be on the daytime shift. It's like, great. And so I've been slowly eking to be awake at night. I take a flight that left JFK at midnight. I landed in San Juan at, 5:30 in the morning. And then I got off the airplane and I went immediately to the debrief from the flight before from the mission and started working. And so that airplane takes off at night, 7 p.m. There was pre-flight at 5 p.m. And since I was not in the actual aircraft, I wasn't on crew rest. So my job during the day was practically to get everything else ready to analyze data, transfer data, while the flight crew, because they were on crew rest, right? They actually had to legally and mandatory relax during the day, take naps by the pool, working frantically. They would take off, I would grab dinner, and then we would wait. Depending upon the weather, they may come back in 4 hours, 8 hours, right? And so I would probably catch a cat nap for 3 hours, wake up, and then go to the airport at 3 in the morning, wait for them to land, debrief, get ready, and then you would get sleep here and there. It was very exhausting. It was waking up at 3:30, go outside, sucks. But when seeing it's like your airplane coming down at 4 in the morning, for a disaster response, you get that surge of energy there. And so that's very rewarding. It's certainly not easy. It's certainly hard. It's not for everybody. But rewarding is, I think the correct word to do there. And not everything rewarding is fun.
Okay, thank you. The next question. Since images can have a lot of noisy data, how do you choose which features are most important to eliminate noise and still result in correct predictions?
So I don't necessarily want to eliminate noise. I want to be able to be robust to noise. The two images, I shown today are, these are good photos, right? The photographer who took this photo did a very good job. The color's right, the lighting's right, the lenses aren't smudged. There are plenty of photos that are not like that. And so what we want to do is, really focus on that diversity of features and the consistency of it. And so if I have enough images that say have rubble or damage in it, I know in this data set that the perspectives, the lighting conditions of rubble will be very different. And so I'm getting the consistency, that very narrow focus of the damage label. However, because I have a diversity of different ways that damage and rubble can look like, that is really the robustness to noise comes into play. We're trying to teach that, rubble does not always look like a bright, sunny California day under these lighting conditions. And so this is really where you don't want to overtrain or bias your model one way or another, but really the importance of having that, wide type of data set.
Okay. From an AI standpoint, why wouldn't something like the classic ANN digit recognition example work for the task of labeling what we see here? That is, we turn these pictures into a row of pixels and get a discrete output with an ANN.
So it's not, the classical approach here can work, or it could be really as a part of one way that it could work. What you often see for low altitude imagery, this type of perspective, that many of the classical techniques start to break down. And so we originally looked at applying algorithms and classifiers designed for satellite imagery, which are incredibly pixel based. And we were not getting great performance. So one, the oblique perspective of this data set is rare. Satellite imagery is often nadir, so top down, so you'll see it's just the tops of the roofs. And then if you're, say, a lot of the commercial market, you're kind of at that 90 degree, you're looking face on, so you're looking at the side of the building, street level, if you will. With ours, because it's low altitude, generally below 2,000 feet AGL, often below 1,000 feet AGL, and because it's from the oblique perspective, you both see the top and side of the houses and potentially multiple sides. That perspective can challenge many of the classical pixel-based techniques. Additionally, many of the pixel-based techniques can be computationally intensive. And so once again, think about, right, I wanted to play this on a drone, embedded hardware, and ultimately, I don't necessarily care always about, the minute pixel level features. I care about, first, is there flooding in this image? We looked at commercial classifiers, and they're not good at even saying if there's flooding, let alone where flooding is. And so this is, high level. Okay, let's figure out how to label flooding consistently. And kind of just to go back to the previous question, flooding can look very different. Here, flooding is brown. So if you're doing a pixel-based kind of an RGB map, color map, you're gonna have a lot of brown and green. There's a lot of other things that could be brown and green that are not disaster related or flooding related. I don't have it in front of me here, but we have another image that looks somewhat similar to this. So brown, green, and one of the commercial classifiers labeled it as a toilet. If it saw a lot of brown, muddy water, you know what? That from what it was trained on, a toilet does, conceptually make sense from one of those pixel RGB type approaches.
Okay, essentially, were the tools used to created in collaboration with AWS and MIT?
So majority of the tools were developed, what we present today, were first funded under a NIST grant in partnership with the New Jersey Office of Homeland Security and Preparedness and MIT campus, and then Lincoln Laboratory as well. Amazon Web Services were not involved in the original program. We started our engagement with Amazon Web Services, I believe in April 2019, when we started looking at Mechanical Turk for the annotation, and then that led to the engagement with the public dataset program. Amazon Web Services is currently funding an educational initiative through the Beaverworks Center at MIT campus that leverages the LADI dataset. But the tutorial, the development of the dataset, that was, they were not explicitly involved there, other than we were using their services. Content that I didn't talk about today, they definitely have more of an involvement in.
Okay, our next question is that NIST Analytics owned by Juniper?
I don't understand what is being asked with NIST Analytics. I think, is it NIST Analytics? Are you referring to a Jupyter notebook?
Juniper.
Right. Mark, can you, in the question and answer, clarify, are you referring to like a Jupyter notebook, or provide another sentence or two? And we can then.
He said you referred or referenced NIST, M-I-S-T.
NIST. NIST.
I think NIST is the National Institute for Standards and Technology, which is a government agency.
Yeah. It's in the chat, the Computer Vision Challenge.
Our next question, what model or backbone are you using to get the 80% accuracy?
So if you go to the LADI tutorial, this was an early version of it. Our latest one is not up. We primarily used a basic, we took ResNet, which is arguably one of the top 3 open source frameworks. We used a ResNet model, and then with some targeted annotations and tuning, we get about 79 to 80%. There are other papers out of that NIST challenge that, depending upon the feature, got better performance. This is not a simple question. What we're looking now is a little bit more of a advanced approach beyond ResNet. So our first step was make the data set. Okay. Step 2, let's make a baseline classifier. All right. So we're going to throw it at ResNet. All right. We got better than 50% performance, right? There's hope. All right. Let's try a little bit with ResNet, right? Open source. That's about that 75 to 80% that I mentioned. But we're starting to see diminishing returns on that approach. And also now that, we've started to play around with the data and the classifiers, we're starting to get a better sense on, what different avenues we can take to improve performance. And so now we're currently looking at a combination of both one-shot learning and then also more of this semantic label space. We previously published a paper looking at how do you treat this problem similar to like a natural language text problem, things with bag of words. We think we called it like a bag of labels. And that's, going much more into, I would say, the computer science-y end of data science. My collaborator is, I would say, he is the more AI ML knowledgeable out of both of us. And so how this often worked was the bag of labels and some of the other approaches. So, well, how about we approach the problem this way? And so very similar to kind of the way I spoke here. But he was the one who really would say, okay, deep down underneath the hood, this is what's going to work, biases and things like that. And so you're not an island. I think another great lesson here, right? Find collaborators that really work well with you, because that's really how you're going to make things happen. The one-shot approach actually came from, we kind of thought about it, but another researcher said, hey, have you tried this? And he kind of put something together, played around with it, and we're like, oh, that kind of worked. And so now we're going to adopt that into there. This is, right, it's research. We don't know the answer. This is actually, I think, one of the more why I like being a researcher. You have a very clear question, classify flooding well. But how to do it, it's not, it's not black and white.
Okay, Michael adds to his question. He says, I was looking at the ImageNet list and the efficient net-L2 got 98% in top 1 and 0.08% in the top 5.
Yeah, so we have looked at ImageNet. I think one of our baseline classifiers is ImageNet based. Very similar to ResNet and YOLO based. They're very good at things, but when you start throwing things like, when you start throwing stuff, particularly rubble, flooding is really tough. Their performance drops. What you'll often see is you may see single focus papers saying, we did a really good job on classifying X damage, or not even damage, it's usually rubble. But they develop their training data set or their classifier is so tuned to that one thing that questions like, well, I wanted to apply a different related feature to it. Those models start to break down. And so, yes, a lot of these systems are very good at very specific things. I think if you're really interested in disaster response and kind of traditional threats, the XView challenge by BIDUX is a great example. Like, they do some really awesome things. But XView is predominantly satellite imagery, XView 1 and 2, and very focused on infrastructure, building damage, building rubble, flooding, more of these type of stuff features is not very prevalent in that challenge, nor in that data set. And so that's, once again, as a data scientist, we look at where can we make the biggest impact and devote our resources. Low altitude oblique, it was a perspective that was not well representative in the data set community. And right, we we showed you, we put up the commercial classifiers and those did not perform well. And then stuff. So flooding, rubble, things like that to shore those advances up as well.
Okay, our next question. General career question rather than something specific to disaster response. After graduation this May, I'm going to be in a technical rotational program. My question is, in your opinion, how important is it to be open to all different types of data science / tech roles? Did you know exactly what you wanted to do after college? Thanks for any input you have.
Yes and no. I always liked airplanes. I always liked robots, even as a kid. And so I wanted to do something with flying robots. The word drone didn't exist yet. I went to undergraduate, was involved in the Aerospace Society, got my background, and I was hired as an intern at Lincoln Laboratory to work on drone airspace integration, and then I was hired full-time. And I've been at the lab ever since. So I knew the problem or the use case I wanted to do. I'm very lucky that I can, go back in time and talk to, 5-year-old Andrew, be like, you did it. You're still working on flying airplanes. 5-year-old Andrew had no clue what he wanted to do with flying airplanes, robotic airplanes, but he thought they were cool. So that is my domain. What am I interested in? That is not a technical role. I didn't know my technical role. I definitely bounced around a bunch in undergraduate what I thought my technical role would be. And I knew eventually I would want to go to grad school, but I didn't know what. And so when I started at the lab, there was a bunch, I'm bottom of the totem pole, fresh out, right? You're going to turn the crank and you're going to learn a lot. And based upon that, I decided I liked more of the systems engineering and information theoretics approach. Data science, once again, when I was in grad school, was just starting to become a term. My master's degree is in electrical engineering, and I never took electronics class. I have an optimization background, so more of a classical machine learning background, but my master's thesis focused more on the information theoretics on, what pieces of information are useful from both a computational standpoint and from a, solve the answer standpoint. And so hopefully, my talk today reflects that. This is inherently an applied mathematics degree. I hated math in high school, and I hated Calc 1 and 2 in undergraduate. I enjoyed Math 220 matrices at Penn State. It was my favorite math class I've ever taken. I think it's actually one of my favorite classes I've ever taken. And I like that. I learned that I like linear algebra. And going back in time, I would have thought I was crazy to tell high school me that you have an applied mathematics degree. I really didn't like it, but I found something that I really liked. And here I am effectively as an applied mathematician at this point. And I will never, ever say I'm a full mathematician. I think even applied mathematician is really pulling it. I do linear algebra, but try different things. And you may find the things that you hate or that you think you hate. There may be a slice of it that you really like, and go from there. Other things that I really thought besides it, I really thought about a computational geometry degree background. Once again, trig, geo, very math-based. And so, yeah, you'll never find out. Don't feel rushed or pressured that you need to know immediately what you want to do after undergraduate, because you will, right? You don't know what you don't know yet.
Okay.
So Andrew, I have a few questions.
Sure.
But first, thank you very much for a stimulating talk. In our classroom teaching, we often focus on the methodologies, but it is eye-opening to see the real-world challenges when you deal with real-world problems. And I totally agree with you that data science is not everywhere. That's also why in my course, we ask students to familiarize themselves with the literature of data science being applied to other domains. And by the way, I went to Lincoln Lab maybe more than 10 years ago. It was a great experience. I think it's a very nice place to work. So my first question to you, what skills, either technical or non-technical, does a data scientist today need to possess in order to be successful in your workplace?
Reading. So like I said, data science, or when you become over a team, right? A good team will have a mix of different roles and technical expertise. Knowing yourself is a good part of helping build out that team composition. And so depending on the project, I may wear different hats, but I still have my own style and expertise. And so the way I approach the problem is certainly different, but oh, Andrew is good at or known for this, or so-and-so is good and known for this. And so really understanding yourself and your expertise, like, are you going to be super mathematician in computer science and really underneath the hood? Or are you going to be really good at visualization and, showing different slices and dices of data? Those are technical skills, but then there's also, I would say, more of these programmatic skills. Are you really good at engaging the end users of your technology and building a rapport and really talking to them to learn what they need, and not you pushing a solution on them, but listening on what they need? Are you a good reader? And so I will show, this is actually one of my tabs I have open. I read a lot. It's something that you have to kind of commit to. So I have a paper here that I'm reading about driving fire behavior from UAS imagery. Here's another paper I've been looking about weather hazard risk quantification, right? So these are more modern papers. I've been reviewing the historical chronology of the FAA, because I was trying to learn about where the specific regulation and kind of intent was born out of historically. And then, I have another kind of just general blog post cutting something out. I think one of the skills that has really made me successful and really benefits my team, right, is the reading. And I can kind of go into a room and be like, oh, how about this paper if they tried this, right? And it's not right. I'm not looking at every single paper at a deep technical detail and understanding it, but I'm really trying to, from my perspective, understand the lay of the land. Where is research and technology is advancing and moving? What are people focusing on? Were they able to solve a similar problem and get a performance that I'm interested in? This fire behavior paper was actually really interesting to me. So I emailed the authors and like, hey, can you send me your data? And then I got their data and I was able to do something with it. And so, like I said, you really need to know yourself. What really has resonated with me with some of the, I really like literature review. I like the historical understanding where things come in. And my research style, my personal engagement with others, this kind of programmatic / tactical skill works well. But it doesn't, necessarily have to work well for you. Like I said, know your strengths and then really kind of lean into it to, help you make yourself stand out, but also I enjoy reading technical papers from the 1950s and 60s. And so that is something I was able to incorporate into my day-to-day job, which was great.
I'm really glad you mentioned the importance of reading. In my course, much of the course is about reading the literature, and every semester I hear some students saying that there's too much reading in this course, but I'm glad that you mentioned how important it is for a data science student to be able to read. My next question, in data science, we often cannot prove what we do is correct, right? Unlike in traditional mathematics, you can always prove a theorem. So because in data science, we have a lot of assumptions we have to make in our models. And the data we collect may also not be representative. So how do we convince our clients, right? What we do is really highly valuable to them, even if we cannot prove anything.
So be honest and don't oversell. Overselling is it's bad for you, it's bad for the client, bad for the community. Now I will admit that, I'm at a nonprofit, no conflict of interest, so I can kind of wear this hat easier than say others. But ultimately you still want to be honest, right? Like I said, we know the performance of our classifier and this is it. And no, it's not ready for prime time. And when we do get a performance that we deem acceptable, we need to be very clear, like this classifier is going to be good, should be good for XYZ. Do not use it for ABC. The client will probably use it for ABC. And so you need to think of ways to mitigate that, or how to best incorporate that into the workflow. We don't know. And so, like I mentioned, I've been working on this LADI data set 4 years now, from the initial concept, right, when the NIST funding, actually started flowing and I was able to charge to it. And we're not at an operational classifier. I'd be thrilled if we get a prototype one this year. And so I think since we don't know, and especially depending upon your use case, things take time. Be patient. Now, this is not going to be a black hole, right? You need to also know when you got to cut ties with it, and then maybe come back to it. And I know that's really hard, especially as an undergrad, to see that. I think the best way to summarize this is neural networks, DNNs to CNNs. The fundamentals for that were proposed decades ago. 80s, I think even far back to the 70s. The problem was when they originally proposed, we lacked the computational resources, the GPUs that we take for granted today to actually train a DNN and CNN. And there was actually papers in the 90s that say this is never going to happen, right? It's a great idea on paper, but we just can't do it. Well, the iPhone happened, embedded computing really took off, and then, oh, we have the compute horsepower now. And then a machine learning technique that was honestly largely by the wayside is now, the foundational element to a lot what we do in modern research and industry. And so people cut ties on it decades ago, and now it's back in full force.
Thank you. And my last question, in our course, we also give students access to AWS, and in particular, their SageMaker machine learning toolbox. So how important is it for a data scientist in the real world to be able to use cloud services such as AWS? And do data scientists today still build and operate their own clusters and do their own, algorithm programming besides plugging, existing tools?
So I am familiar with SageMaker. We have looked at, we are using SageMaker for our LADI project. We have only recently transitioned to the cloud for this. Everything I presented was done on-premise or local compute. And now that's both at an organizational level, often. So at MIT and Lincoln Laboratory, we have one of the top supercomputers in the US. Yeah, you better damn well sure I'm using that because that is free to me. And so how you do machine learning, how you do the storage, kind of the compute and storage optimization, say on an on-premise distributed supercomputer, is actually totally different than the way you do it in a cloud environment. And so now, and I don't have to pay for that, right? That is out of our overhead, right? That's a resource available to me. And it's awesome. Now, the crowdsourcing, the annotation is not something I can do as well locally. And so that is where we're starting to use SageMaker and some cloud services. And so cloud costs money. And so when you're really kind of getting ready, and I'm familiar with Lambda functions and all of that on AWS, a lot of that you can prototype on your local machine. There is no need to immediately go to the cloud. Get your gut feeling, right? Work local on your machine. That's free. If you have any compute capacities at your organization, I recommend going there next, right? Know your data. And then from my perspective, right? Because once again, I have this great on-prem, then, okay, let's start talking about the cloud, more of an operational capability, uptime and things like that. Often a lot of the cloud niceties about the cloud, about uptime, backup, all of that scalability, you don't need that necessarily when you're doing the initial research, right? That's more of an operational real-time things that you need once you get there, but they're not things you need right away. And so, yes, the cloud has a role. Yes, on-prem has a role. But similar to what I've been talking about today is know what you're trying to do and be efficient rather than say, oh, we always have to go to the cloud or we always have to do on-prem, right? As all things, it depends.
Okay,
Andrew,
thank you.
I missed a question.
Sure.
This was from Aaron. He's saying, why can an 80% accurate model not be partially utilized by the disaster response team? Depending on the proportions of type half error, it could act as a precursor filter before having humans look at the images to confirm or deny the classification of the damage. Could you please discuss a bit more on the model accuracy?
So class ends at 11. I have 3 minutes to do this.
Sorry about that.
No worries. So we worked, I've worked with joint field offices, and I was at FEMA headquarters when Harvey was making landfall. I think landfall. They are human intensive workflows. So to introduce new technology there's a very high bar. And so you need to be able to then also train people to use this. So what you just described, was as a technical person, right? As a computer vision background, I knew exactly what you're gonna say. Imagine going to a FEMA analyst who has no technical background in computer vision, and you need to explain to them, okay, here's something that's going to be wrong 20% of the time. And then you need to also tell them it's going to be wrong what? Is it going to give you an image that is incorrectly labeled? Is it a false positive, true negative? You have no chance to get that adopted. In that, remember, this is, they have to make decisions. We're talking about very time-sensitive cases. So while 80% sounds fine, it's the legs and tails of it. How do I integrate technology so that's adopted and used? And also where I'm not missing something. Imagine, a great way to think of this is New York Times headlines. Imagine you're 80% right, but you have a horrible false negative rate. So you miss a lot of images that you should. Can you imagine the backlash that your system would get saying this system did not filter, this system filtered out or did not show me this image of, this family on a rooftop? That's not good. Now, once again, disaster response, right? There's both a technical and political and societal implications in it. But do you really want to go into FEMA headquarters and say this classifier will miss families on rooftops? Or it will show you images that are completely fine and it will slow down your work. And so we are not comfortable at an 80% solution to do that.
One last quick question on top of that is what % is acceptable?
I believe under certain use cases, 85 to 90% gets us into that shadow mode operation. I believe at that, I hypothesize, at that we can start socializing it, and we'll more importantly know our true positive, we'll know the biases and assumptions of that system. And that will also enable us to build something on top of it to catch it. And so it's not just 85% computer right? What is the precision or the accuracy of the classifiers? How do I get that answer to an end user so they understand what that 85 actually means, or that 90% means? And this is part of customer engagement. And that's our goal this summer, is to get that bumped up. But 80% is, we're not comfortable with there yet. I'm not even sure if they'll even adopt 85. I think 85, we can start having a discussion and up.
Okay, thank you very much. I think that concludes the talk. And hopefully in the future, when the pandemic's over, you will be able to come back to Penn State again.
Thank you for having me.